Hey, welcome back, Math 30-1 students. Today we're looking at rational functions. So we covered radical functions in the last two lessons, and today we're looking at rational functions. Now, what is a rational function? It's a function that takes the form of f of x equals n of x over d of x, where n and x and d of x, the numerator and denominator, are both polynomial functions. The only condition is d of x can't equal 0, otherwise we'd be dividing by 0. Okay, now also the degree of d of x needs to be greater than 0. Now what they're referring to there is basically if you just had a constant in the denominator, like 5 or something, then it wouldn't be a polynomial function. It would just be a linear quadratic, something like that. Okay, so examples of rational functions, each of these. Notice how each one of them has some form of x in the denominator. Okay, and you have touched on this in previous courses. We're just going to look at it in more detail now. Okay, discontinuities. Since rational functions are really just fractions, the denominator can't equal 0. And if it can't equal 0, that means there's going to be values of x that are non-permissible, okay? So a value that would not be allowed. Now I said value for x, it depends on what the variable is, so whatever the independent variable is. All right, let's take a look at what the non-permissible values would be for these examples they gave us here. So what you do is you let the denominator equal 0, or say cannot equal 0, and then you solve it like an equation. So add 1 to the other side, that would mean x can't equal 1. Or this one, x squared minus 9 can't equal 0. In this case, we can just solve for x, but sometimes you might have to factor that to figure out the x value. But here we can basically move the 9 to the other side and then square root both sides, and we get plus or negative 3 would satisfy that equation. Okay, for this one, and that's cannot equal because we're doing non-permissible. Okay, for h of x, set the denominator cannot equal to 0 and solve for x. So therefore x cannot equal negative 2. So that's what they're referring to here, the non-permissible values for each one of those functions. So not all rational functions have non-permissible values, believe it or not, because you could have something like this. F of x equals 1 over x squared plus 1. And if you'll notice, whatever value we put in for x there, when we square it and then add 1, that would never equal 0, right? So in this case, we would have the graph of a rational function would become a continuous curve, okay? But if it has non-permissible values, then there's some sort of discontinuity in the graph. And we're going to be learning about two types of discontinuity in Math 30-1. One is an infinite discontinuity, which leads to a vertical asymptote on the graph. And the other is a point discontinuity, which basically leads to like a hole in the graph. Okay, in this lesson in particular, we're going to be looking at infinite discontinuities or vertical asymptotes. And we're also going to look at horizontal asymptotes as well, just to help us with the behavior of the graph. Okay, let's look at the next lesson, or next page. Okay, so we're going to graph a rational function here using table of values and kind of look at what happens there. Consider the rational function f of x equals 1 over x minus 1. Now, since we can't divide by 0, right, division by 0 is not defined, the non-permissible value of this function would be, okay, set that denominator equal to 0, or cannot equal to 0, solve for x, which means the non-permissible value, oops, why did I put negative 1? It's just equal to 1. Alright, complete the table of values below, plot the points on the grid, but do not connect the points at this time. Okay, so what you're going to do is you're going to fill in this table of values. Just remember here, f of x is equal to this function up here, which 1 over x minus 1. So go ahead and put that value in, each of these values in for x into that function, and determine your y values. Okay, so you go ahead and fill those in, fill the table in, plot the points, but don't connect them yet. All right, so pause your video. Okay, so we filled in that table. You'll notice when x was 1, it was undefined, which of course was our non-permissible value. And then we plotted those points. We're not going to join them up yet because we're going to investigate what is going on basically near x equals 1, because it looks like the graph is kind of starting to head down, and then over here it's starting to head up. So we're going to take a look at the behavior of this function near that non-permissible value. By doing that, we're going to be subbing in values very close to it. So 0.5, 0.9, 0.99, kind of approaching from the left side, that x equals 1, and then we're going to approach it from the right hand side as well. So why don't you guys go ahead and fill in this table of values, say to 2 decimal places or something, and if you can, and then we're going to discuss and actually you can go ahead and plot the points, and then we will connect them and discuss the graph. Okay, so pause your video now, please. Hey there, sorry about that. I was distracted before we paused the video. Of course there'd be no decimals on these ones. So we sub those values in, and I just wanted to make sure too that you guys are able to do this quickly by not having to type it in every single time. I'm going to bring up the calculator and show you the second enter button. Maybe you know it already, but in case you don't, this can shorten things up. So let me just grab the calculator. Okay, so we type in the first one there, and we went 1 divided by 0.5 minus 1, and then we hit enter. And then we want to do the next one, but do we really want to type the whole thing in again? You can just go second enter, and it brings up what you just typed in, and you can go several commands back just by going second enter several times. And we want 0.9, so we hit enter, and there we go, -10. Okay, now second enter again and go back. Now we want 0.99, but we kind of want to insert a 9 there. So we're going to go second insert and 9. So that's under the delete button. Hit enter, and there we go. And then you can do it for the other values as well. So now we're going to plot those points. I imagine you guys have already. So I'm going to do that and pause the video, and then we'll take a look and see what we have for a graph. Okay, so we get a graph kind of like this, and we can verify that with the graphing calculator as well. But as you notice, that it looks like the graph will never cross that vertical line of x equals 1. It will get closer and closer. As we get closer and closer, we just keep getting larger y values. So let's also talk about what's happening at either end of the graph here. As x gets larger and larger, it looks like our y values are getting very, very close to what number? Well, it looks like that the y values are approaching, but not equaling 0. Okay, so as x approaches infinity, y approaches 0. And if we look at the negative infinity, so as x gets very large in the negative direction, again, it looks like our y values are getting closer and closer to 0, but not quite touching it. This time on the negative side, though. Again, y approaches, I'm going to use the arrow for that, y approaches 0. Okay, so let's choose some options here. Let's talk about this. So correct alternate, as x gets closer and closer to non-permissible values of 1, so we're talking about the vertical asymptote here. The value of the function approaches, from the left. So from the left, it looks like we're approaching really big negative values, so negative infinity. And as we approach from the right, we are approaching really big positive values for y. And that was the situation for this graph. That's not necessarily true for all graphs. Okay, let's look at the next page. Okay, so basically, I kind of jumped the gun talking about an asymptote, but an asymptote is basically a line that a curve approaches more and more closely to as, you know, the values of x or y approach a bigger value. So basically it's what we're approaching, but we don't cross, especially a vertical asymptote. Okay, so as x gets closer and closer to 1, the value of f of x gets closer and closer to the line with the equation of x equals 1, but we'll never reach it. So this is a situation where we have an infinite discontinuity at x equals 1, and therefore the line x equals 1 is called a vertical asymptote of the graph of y equals f of x. Okay, and this occurs because 1 is a 0 of the denominator in the rational function. We had 1 over x minus 1, x can't equal 1. Okay, now as we approached positive and negative infinity, the graph got closer and closer to y equals 0, but it will never reach it. in this situation, y equals 0 would be called a horizontal asymptote. And it's not an infinite discontinuity because every x value exists. That's just a y value that can't. And actually, that's not true. The y value of 0 can still happen. So we can cross a horizontal asymptote, but this is simply what the graph approaches as x gets very, very small, like negative infinity, or very, very large, positive infinity. Okay, so typically these asymptotes are represented on graphs with dashed lines. Sometimes the calculator has issues graphing them properly. We'll talk about that later. Okay, let's investigate 3 different graphs here and the asymptotes of them. So first, consider the function y equals, or f of x equals 3 over x. State the domain of the function. So when you look at this, what do you notice? X really is in the denominator, and therefore what's our non-permissible value? That's right, x can't equal 0. So that means our domain would be x can't equal 0, but it could be anything else. So we'll tack on x's an element in the reals. If we want set builder notation, we would show it like that. Okay, so we're going to use a graphing calculator to graph the function, but for now they don't want you to sketch it on the grid. And then we're going to get the equation of the vertical asymptote from not only the graphing calculator, but also what we found out for our domain. So let's grab the calculators and graph this function, 3 over x in y1. Okay, so with our graphing calculator and with our windows set to zoom standard, so negative 10 to 10 for both x and y, we should end up with this. Now you'll notice that our graph seems to be getting closer to but not crossing either of the axes. So in particular, the vertical asymptote then is likely the y-axis, which would have an equation of x equals 0. And look, what was our restriction on our domain? X can't equal 0. Okay, coincidence? I think not. Okay, so we're going to show that on our grid as a dashed line on the axis. I know it's not easy to write it right on the axis. Okay, so that's our vertical asymptote of x equals 0. Okay, now we can complete drawing the graph, which basically looked like this. Okay, and like this. And there we go. Okay, state the equation of the horizontal asymptote. So you probably noticed that the graph also seemed to get closer and closer to the x-axis, but wasn't crossing it. Well, guess what? That means our horizontal asymptote is y equals 0. Okay, the x-axis. Okay, and as a result, state the range of the function. Well, if it appears to not cross the x-axis anywhere, like not even in between, that would mean the range would be y can't equal 0, but it can be anything else, so y is an element in the reals. Do you need to write y element in the reals? You betcha. You have to write this. If you've only stated what it can't equal, you have to state what else it can equal. Okay, so let's take a look at the next example. Okay, on the next function, we have 2x over x plus 1, and they want you to start off by stating the domain again. So, once again, denominator can't equal 0, so therefore x can't equal negative 1, and our domain would be that x can't equal negative 1, but it could equal anything else. Okay, grab your graphing calculator, let's take a look at what that looks like, and then we'll figure out what the equation of the vertical asymptote is. And you guys go ahead and do basically B, C, and D, and we'll resume the video at E. Okay, so pause your video and see if you can get those 3 done. Okay, hopefully you have the same graph as I do. If you don't, something that might have happened was in your, when you put it into y1, if you don't put brackets around the denominator, numerator as well if you have terms being added and subtracted, but for sure the denominator with the adding and subtracting, it will actually only divide 2x by x and then add 1 to the whole function. So make sure you have brackets around your numerator and denominator. Okay, so we get this graph. Our vertical asymptote appears to be at x equals negative 1. Now my graph did this weird little line there. Really the line is not part of the graph. It's sort of like a barrier the graph doesn't cross. Okay, now estimate the equation of the horizontal asymptote. So it looks like this graph is approaching something, okay, some invisible horizontal line, and we could get that by looking at the table feature. Okay, so let's do that. We might have to finish that up in part 2 of the video. So I'll maybe see you guys in part 2, and we'll look at the horizontal asymptote in the table feature. Okay, so we'll see you there.